So let's go ahead and get started on time, and we'll want to be staying on time throughout the meeting. I'm Mike Patterson, Director of the US CLIVAR program. I know many of you, but I look forward to getting to know many of you, particularly those of you who work in the coastal science arena that I haven't yet met over the course of the next few days. So welcome to Boulder, welcome to UCAR facilities here, and welcome to the workshop on optimizing ocean observing networks for detecting the coastal climate signal. This topic is right in line with US CLIVAR's interest in coastal climate that was outlined in a report, a white paper report issued in 2021 that provided motivation, the scope, and objectives for a 10 to 15 year research challenge, noting that we won't be done with understanding climate at the coastlines within 15 years, but with a concerted effort over a 10 to 15 year period, partnering with other programs like IOOC and in particular the IOOC regional associations, that we could make significant progress in collaboration. And this workshop is a cornerstone, I think, to that collaboration in helping to identify the needs for climate information and the ability of our observing systems in the coastal regions of the US to address those needs. And so in US CLIVAR, this sits squarely within our interest in understanding the role of the ocean in climate variability and change, and in particular, the impacts of the larger scale climate system on regional and the regions along our coastlines, and how signals are come in through teleconnections from the global ocean, as well as understanding the climate and weather phenomena that are modulated, including sea level rise, coastal inundation from coastal storms, including tropical cyclones and extratropical storms that impinge the coast, and marine heat waves, and importantly, the interaction of the physics with the biogeochemistry and the impacts on marine ecosystems and fisheries. So this, again, observing system is cornerstone to climate science, and I look forward to the deliberations over the next few days to help map out, building upon what we have in the ocean already for an optimized observing system that will meet the needs for understanding climate variability and change in the coastal zone. So with that, I'm going to hand off to David Legler. David's the director of NOAA GOMO program. Many of you probably know him, and he's co-chair of the IOOC task team for coastal climate signals. So David.
Thank you, Mike. Sure. Thank you very much, Mike. And I want to thank Mike and the organizing committee who stuck with it all these months in planning. It's been a challenging time to organize this, but it's for a very important topic, as Mike just elucidated. So I'm David Legler. I'm one of the IOOC co-chairs, the Interagency Ocean Observing Committee. There are 4 co-chairs, myself from NOAA, Laura Lorenzoni from NASA, Lisa Clow from NSF, and Darren Babrock from OSTP. So with 4 co-chairs from those 4 agencies, we are all very well interested and invested in the outcomes of this workshop. We look forward to the discussions and the presentations, and we're going to have some time on Wednesday to talk about the deliverables from the workshop and how that might interleave with what the agencies are looking for. So we'll look forward to that, and thank you all for participating, coming to the workshop. So with that, I'll turn it over to Robert. Thank you.
Well, thanks, David and Mike. So I'm Robert Todd from Woodsell Oceanographics. I'm one of the 2 co-chairs of the organizing committee. So we have a fairly large organizing committee for this meeting that's been working over the last year plus to get this organized. Natalie Cordero-Quiros is the other co-chair. She unfortunately couldn't travel to come here, but she's with us on Zoom. And then Seth Danielson, Manu DiLorenzo, Tommy Moore, Jan Newton, and Dan Rudnick, most of whom are also here, are the other members of the steering committee. I want to point out all of the program organizing committee members. So Alyssa, where are you? Alyssa in the back. Mike, we just heard from. Cassie's also in the back. Nick Rome, we're here. Shelly, who actually, where are you? Because I haven't met you. She's out front. Shelly's out front. And Carrie Dawn Solner, also not here. Okay. So these are the folks you want to go to for the more logistical questions. So again, of course, thanks to the organizers. So this workshop is being supported by basically all of the key funding agencies and through the IOC and IOOC. So what are we here to do? So first, this is in part some definitions as well. So what do we mean by a climate signal? So the working definition we're going with here is that a climate signal links the broader sort of global scale climate changes to their impacts, which may vary between coastal areas and the open ocean. Why are we interested in this? Of course, as the ocean warms, large marine ecosystems and adjoining coastal communities will become more vulnerable to climate change, and developing frameworks to better connect what's happening at the larger scales in the open ocean to the coastal impacts is really an essential part of further developing the observing systems. For the purposes of this workshop, because in 2.5 days we certainly can't cover everything, we're taking coastal to mean from the coastline out to the edge of the EEZ, the 200-mile mark. And our focus will be on from the physics up through the lower trophic levels. So we're not going to try to go all the way up through fisheries. It's a much larger problem at that point. So that's not to say that other things are not important, but that's where we're going to try to keep the focus for this workshop so that we have something tractable. So as Mike mentioned, there was a previous report came out through IOOC 3 years ago now. And hopefully you had a chance to look over that prior to the meeting. I'll just briefly put up here the main recommendations coming out of that report, and I won't even read them all, but the ideas were to expand our coastal observing efforts and our modeling efforts alongside that at the regional scale, to recapitalize and modernize the infrastructure that we have, to invest in technological innovations, to expand our data integration services, and to increase engagement. And so we're going to, through this workshop, we'll be tackling some of these particular recommendations, including how to expand, what we need to invest in, and also by virtue of having everyone here, we're hoping to really increase that engagement across the various groups that are interested in these problems. So our objectives here at the workshop are to identify opportunities to accelerate our co-design of an observing system. We're not going to redesign the observing system in 2.5 days. Just not going to happen. But we will identify ways we can start down that road, bridge the gaps between the global climate research efforts and the more regional, more operational work that many of us in the room are involved in. Foster collaborations between all the different parties that are here. And ultimately, as an outcome of this workshop, is to deliver a set of recommendations, particularly to that IOC task team that David's chairing. So how will the workshop basically be set up? So today is about where we're at now and what are the gaps. So this morning we'll have a few talks, and then this afternoon we'll spend in breakout sessions identifying those gaps. Tomorrow is about what we need. So what do we need moving forward and how do we get there? And then on Wednesday morning, we'll come together and try to wrap it up into a set of recommendations that will ultimately be the ultimate conclusion of the workshop coming out of this, or the report coming out of this workshop. So workshop philosophy. So as mentioned, so we have people, a wide variety of people here across career stages. We have a nice chunk of students through early career and mid and late career individuals. And we have folks that are across the disciplines as well. We have, as far as attendance, about 2/3 of us are here in person, but we also have 1/3 of the participants are online. We do want to make sure everyone is heard. We want to be nice. We want to be respectful. We want to take in all of the various opinions. Particularly in the breakout sessions, we really want to encourage everyone to participate and get their input in. That especially goes for our early career scientists that are here. Please do speak up. Please ask questions. We'll have lots of open discussion time as we move through the agenda. And also we only have a limited number of talks, so we have time for lots of breakouts, but we do have a whole lot of posters as well, and those are a big part of giving everybody a chance to show where we are at now and what people are doing across coastal observing and modeling. So particularly because this is a hybrid meeting, and by now I think everybody's done lots of hybrid meetings, but just a reminder, so for those of us that are here in person, please make sure you're speaking into a microphone so that they can hear you well on Zoom. I know some of us are perfectly capable of speaking very loudly to the room, but Zoom still can't hear that. And try to remember to give your name before you start speaking so people online in particular know who's talking. For virtual participants, please use the hand raise feature for asking questions, and if you can, unmute and turn your camera on when you're speaking so we can see you. The posters are all, so that's actually a question, I don't know, are all the posters, Alyssa, visible online? Or just, okay, even the in-person posters? Awesome. So there you go, all the posters can be online, and then we'll have upstairs is the physical poster gallery as well. So the really important stuff, maybe the most important slide here, there's the Wi-Fi password, or the lack of password. There is elevator access to all the floors. For those who haven't found them yet, the bathrooms, you go out of here, hang a left, and they're in the back corner. There's a lactation room available upstairs. For those who are inclined to such things, feel free to tag these things on Twitter or whatever it is now, or LinkedIn. Tomorrow morning, we'll all smile for a picture to commemorate being here. And there will be breakfast and coffee breaks and lunch every day. Well, lunch on Monday and Tuesday. And again, so if you get confused on building related things, please see Shelly, or for more workshop logistics things, Alyssa and Mike are the ones to go to.
I want to welcome all of you. My name is Jan Newton. I'm from the University of Washington and was on the Scientific Organizing Committee. Welcome people online. We're really glad that you're here too. Okay, so it is my pleasure to introduce session one. We have some speakers. I am co-chairing this with Nathalie Cordero-Quiros, who is also online. Some situation with her travel, and she couldn't be here in person, but shout out to Nathalie, who will be participating, I'm sure, in our discussion. So it is my pleasure to introduce our first speaker for today, an invited first speaker, Dan Rudnick from Scripps. Thank you, Dan.
Well, it's a pleasure. It's a pleasure to be here, and it's a pleasure to see after a lot of years of work that we've gotten to this stage. Okay, where are the things that I'm supposed to push? Oh, here, this one? Yeah. Okay. It's really a pleasure to be here, and it's great. It's been a lot of work. I'm also part of the organizing committee for this, and it's been, seems like years, but here we are. Thanks everybody for attending. All right, what I'm going to do is give a little review of the existing coastal climate system. And here's the outline of what I hope to say. First, I want to briefly answer the question of why we want to measure the coastal climate system. I want to give a review basically in two main parts. First, I want to review US IOOC from the regions. And second, I want to review the GOOS networks, which impinge on the regions. And that, bringing these communities together is actually part of the purpose of this workshop. And so I actually wanted to ask a question. We don't have Slido because we still have to do it old-fashioned way. How many people here identify or are part of IOOC or IOOC adjacent? All right, you could be both now. How many are GOOS people? You could be both, it's possible to be both. So okay, so there is some of both, but it does seem to be more of an IOOC-centric workshop for now. And I think that reflects how it started in some ways. So I'm going to review those two, then I'm going to give a brief view of the US West and East Coasts from a publication that Robert wrote back in the Ocean OBS 19 days. And finally, I want to, start with my hypothesis, which I think is also my conclusion. And that is that the current observing system for the coastal climate signal is a beautiful outcome. I actually had accident in there before, but I changed it to outcome. Maybe accident is better. It's not the result of an optimization. I think that's the point. It has never been optimized for this purpose. It's come together over the years for various purposes. And now we have quite a bit, but it's not optimized. That is my hypothesis. So why do we want to measure the coastal climate signal? Well, society experiences climate change through the effects in the coastal region. Fisheries, transportation, weather, recreation. Lots of applications. Now the science behind it, just a little bit. On the US East Coast, the Gulf Stream dominates the meridional transport of heat and is a major driver of climate variability. On the US West Coast, there's an upwelling system. It's one of the most biologically productive in the world, and it's strongly affected by El Niños, another climate effect. On the US Gulf Coast, the loop current and eddies impact the shelf and the regional ecosystems, other large-scale effects that are being changed by climate. That's just along the continental US. There's effects in the Pacific Islands, in Alaska, in the Great Lakes, in the Caribbean. There's too much to go over. So I'm not going to go over everything. I'm going to apologize in advance for all the things I'm going to miss, but I'll do my best. So this did start with this report in 2021. The way this came about was in 2020, I think a few of us involved in IOOC thought that climate may become more important in the near future in 2020. And we thought we should get ahead of the game and try to state the case for what IOOC is doing in climate. And so the result was this white paper. I think it was a pretty good paper, and I think it got some good attention, and I think it was timely. This is a national issue, but there are regional approaches to this issue through IOOC. I'm going to review some of these next, but one of the outcomes of this report is this meeting. It is this meeting that we would try to figure out how we can do better in the IOOC contribution and ultimately the national contribution to the observing the coastal climate signal. All right, so there's a lot of information. What I did is about a month and a half ago, I asked all the regions for a one-pager on what they're doing about climate. I asked for a map, and I asked for what those regions considered to be the important climate phenomena and what they were doing about it, what technologies, platforms, variables were being measured. And I got almost all the regions gave me something, far too many for me to show. So I'm going to apologize to those regions whose slide will not be here because I only can have time for about 5, but I will put all of them up on the website so we can consider them in one of our breakouts. So they're great information, even if I don't have time to show them today. So NANOOS, this is from Jan. The phenomena, it's a long list, but here I'll talk about a few of them. They're the ENSO, PDO, and PGO, marine heat waves, there's changes in circulation, there's ocean acidification, there's changes in mixing and leads to hypoxia, there's HABs, there's a changing hydrological cycle, and of course there's sea level rise. There's a number of observing platforms, including gliders, buoys, HF radar, shore station, HAB-focused assets, and, and all of these are in this map. And you can see it's a pretty impressive collection of observations. And I think what makes it important is the regions, NANOOS is a great example, but they're all good examples, have great connections with local agencies, local constituencies, and have created systems that work for their regions and are able to detect climate. This is SACORA, so the Southeast Coastal Ocean Observing Regional Association. Again, let's look at the important climate processes. And as you look at these, I will tell you, they were all done independently, and I got them individually, and I want you to look at what's in common. So, more extreme rainfall and heat, rapid hurricane intensification, storm surges, sea level rise, changes in the Gulf Stream, HABs again, ocean acidification again, marine heat waves again. So you can see there's some commonalities that are starting to come out. Buoys, HF radar, gliders, ocean acidification, water level stations, cameras, and a whole list of variables. So some commonalities again. Again, a system built for this region that also is pretty good at observing climate. The Great Lakes. The Great Lakes, the phenomena are understanding winter dynamics, decreasing ice coverage, increasing water temperatures, storm intensities, HABs again, water levels again, lots of commonalities, but specific to this region. They're using buoys, they're using met towers, they're using environmental sample processors. Lots of commonalities. This is for the Great Lakes. Alaska, what are the important phenomena? Ocean acidification, HABs, storm surge, loss of sea ice, of course, marine heat waves, changes in species distribution. What are the technologies? Moorings, HF radar, gliders. There's acoustic telemetry in this case, weather station, water levels, HABs, ocean acidification. You get the idea. A lot of commonalities, everybody doing it in a way that suits their region. And I'm going to close with this last one about IOOC. This is the Pacific Islands. The concerns are tropical cyclones, flooding and inundation from sea level rise, especially a big deal on the low-lying islands of the Western Pacific. Water quality, wave impacts, and the oceanographic changes, again, marine heat waves, and coral bleaching in this case. Buoys, CTDs, sea level rise, gliders, a similar set of tools in a very different place, from example, from Alaska. Similar approaches applied to their region, very similar kinds of concerns. So what are the commonalities here? What do we see from these group of regional approaches? We see, this is a short list, but this is what I pulled out that I thought I really saw in just about everyone. Marine heat waves, sea level rise, interannual indicadal variability, ocean acidification. That's of course a short list we could add to that. Observing approaches including moorings, underwater gliders, shore stations of various types, and high frequency radar. So in a sense, we do have a national system here. It's national in the sense that a lot of the regions are doing it, but each region, to be fair, has optimized in a way that suits their region, not necessarily in a way that is truly national. And I was asked to be a little provocative in the lead up. So here we go. I'm going to provoke just a little bit. And I'm going to say that IOOC has done a tremendous job at serving their regions. I'm going to say that they could do a better job at being a coherent national network. And maybe that's a goal of this meeting. All right, now I want to review the Global Ocean Observing System. The GOOS started in the 90s, and it came out of a climate meeting. That's where it started. It was a climate meeting in the early 90s. And so it was designed, I'd said largely designed, maybe, didn't want to quite say exclusively designed, but certainly at the beginning, it was largely designed to observe climate variability. And CLIVAR, this is where CLIVAR comes from, and on a global scale. So that's where GOOS is. GOOS was about climate from the get-go. It's organized quite different from the way IOOC is organized. It's organized by platform largely by the technology. So there's floats, there's gliders, there's sea level stations, there's moorings. And so again, there's quite a number of networks, far more than I can review today. So I'll review some of them. So first, I have to start with Argo. Argo, in a way, was certainly one of the first ocean observing networks. To me, it's been the biggest change in ocean observations during my career. It's the biggest paradigm changer I've experienced. There was a before Argo and after Argo for global observation of the ocean. The profiles are to 2000. Now they're going to 6,000. They started with only TNS. Now there's a growing list of essential ocean variables, including a number of BGC variables, and just remarkably uniform coverage. It looks like you can walk across the ocean, stepping on floats. This map to me is an achievement of our field. Argo really is that special. It does touch on the coast. If you call the coast the EEZ, the inshore 200 miles, you will see floats in the EEZ. But if I were to zoom in on any particular coastal region, you will see they don't get all the way to the coast. You will see they pretty much set the outside boundary condition. But they're certainly part of the story for climate observation of the ocean, you bet. Something that is on the coast is the global sea level observing system, GLOSS. I guess there's two GLOSSes we're talking about. GLOSS is also the Great Lakes Observing System. This one this predates, I think it's fair to say. It started in 1985, so even before Argo, really. It's got global coverage. It is the standard reference for sea level in the world. There's over 90 countries. The lollipops are showing where some of these stations are. I zoomed in instead of the global map. I zoomed in on the US coast and the Pacific. And this is part of our coastal system for observing climate, a very important part. There is a emerging network in GOOS called Ocean Gliders. One part of that is Boone for the Boundary Ocean Observing Network. There's a number of places where there have been gliders sustained for at least a year. This is the map. These gliders are measuring things like TNS, and I'm just showing here one from California. This is something I've been up to, and it's an example that even now this line is actually funded by IOOC, but it's part of this global effort that's part of GOOS as well. So we already have some ability to crosstalk, often through individuals, but we are already cooperating in this way. This particular map shows the currents off the coast, the mean currents. The red is the California undercurrent, the blue is the California current. I think we've been able to observe this about as well as we possibly can with a network now that is 19 years old with gliders. Ocean Sites is a network of moorings in GOOS. Again, you can look at the distribution. Some of these truly are coastal, and they contribute to observing the coastal climate signal. Here's one in the boundary current. This is from Rapid Mocha. You can see this goes back about 20 years. The wiggly lines are some measures of the Gulf Stream, the MOC, different components of the MOC that are contributing to both coastal climate and global climate. Again, a good connection between the two. Now I want to go over just two slides that I got from an OceanObs 19 paper on the boundary current system that Robert led, to look at two different pretty well observed regions. One is the US West Coast. So now this includes not only the IOOC assets and the GOOS assets, but a whole bunch of other ones too. So this particular one has, as part of it, Cal Coffee. That's a lot of those green dots. Those are ship stations. Cal Coffee is an example of this beautiful historical accident that was started in the 50s, around 1950, to study the sardine collapse. It was actually started by the state of California originally. That has now been going on for 75 years. And I think it's fair to say it's one of the longest, or perhaps the longest running observing system like that has such a wide variety of variables, all the way from physics to biology, all the way to fish. What's also in there are some of the gliders. Those are the orange lines, all the way up the coast, including our efforts off California and the efforts in Oregon and Washington, some of which are funded by NANUS, some also by the OOI. There's a number of time series. Those are the red dots. Those are moorings that are from a variety of funding done for a variety of different reasons. But this is, in essence, the climate observing system for the The West Coast, I don't know how to count how many different funding sources, how many different reasons they started, how many different ways they became, but here they are. This is the beautiful accident of history. And it's actually pretty good. Certainly not optimized in any sense, just happened. Here's what we have in the Northwest Atlantic, the Gulf Stream. We have multi-decadal measurements from ships of opportunity, the Oleander line, out to Bermuda. We have cables at the Florida Strait. We have gliders since 2015. That's the orange lines, a number of time series, and the moorings, those are the red dots, all for a variety of reasons, all for different purposes. There's the OOI contribution in there. I think there's a contribution from Peach in there. And then there's green, there's ship stations as well. So a whole range of different approaches, all for different reasons, but we do have a climate observing system. Okay, so let's talk about designing a climate observing system. Well, the current network, I do think it's a beautiful outcome, maybe accident of history. It is not the result of an optimization. Nobody ever sat down and said, these are the things we need, and that's where they ought to be. That did not happen. So what should we do about it? Well, I think we should honor these legacy systems. Some of them are really good. Most of them are really good. But we have to take advantage of new approaches as well. We have to make this system national. We have to have a national outlook, but we do have to respect the regional priorities. It should really be multi-platform and multi-variable, but we have to respect the existing global approaches, which, the way they're organized at least, are largely by platform. So this is what we have to do during this meeting. So I learned a phrase last week. It's BHAG. Have you ever heard of BHAG before? I just learned it like 10 days ago at the UG2 meeting. So there was can I tell a story? Yeah, so there was a group of kids, they were Lego kids, that their task was to build an underwater glider or vehicle with Legos. And they came to visit us. So they were I think they were grade school kids. And they came in, they were invited and they came. And so they visited us one day. And you know what these kids, there's always the dad, there's the Lego dad, right? Yeah, so the Lego dad, they came in and they were sitting very politely and listening to our stuff. And then at the end, we were summing up, and the Lego dad, at some point, he raised his hand and he goes, "Do you have a BHAG?" And he said, "Well, what's a BHAG?" And he said, "It's a big, hairy, audacious goal." He said, "What is your big, hairy, audacious goal?" Because what he was hearing, I mean, he was like a truth teller brought into our midst. We were nibbling at the edges, we were nibbling and nibbling and nibbling, and he hadn't heard something big. He hadn't heard something important. And so he said, "You need a BHAG." And actually the BHAG we have now we're using that word. I'm using it every day. And so the BHAG that we have now, we decided at UG2 was a sustained system of gliders for observing climate. That's the BHAG that came out of UG2. So the BHAG that we have to aim for here is a purposely designed system for observing the coastal climate signal. That's our BHAG for these few days. Thanks.
So thank you, Dan, very much for that walk through history.
You're there. Let me stay here. Go ahead.
Hey,
Yes.
Jan, we have time for some questions now. We have 5 minutes, so we could take a question or two.
All right, new instructions. We have time for questions. We'll see if there are any questions. You can sit down. That's fine. Yes. And then go to the mic. Thank you, Dylan.
Yeah, no problem. Thanks, Dan. That was an awesome summary. You might have said maybe in your very first slide, and I just missed it, but when we're talking about coastal climate signal, are we distinguishing between variability across all time, like climate timescales, or are we going after the climate change signal, which might be a slightly different network of array?
Okay. Yeah, so I would say both. Would be my answer, is both.
Thanks, Dan, and I appreciate that overview. You spoke a lot about the techniques or approaches to optimizing, and I wonder if you might say a few words around how you think we're doing in terms of defining the sort of variable or environmental parameter space. Because it seems to me, regardless of the technologies we might think about, which are always constantly evolving and changing, do we have a good sense of what the needs are?
All right, so there's two ways. I want to interpret that question in two ways. One is the scientific objectives that we have to address, and I admit I didn't spend a lot of time on that, and I just it's time. The second that I spent almost no time on was the variables, and I had a table of the EOVs at one time, and if you put that on the slide, the type was so small that you couldn't read a single one. So I thought I would not spend the time to go through each of those possible variables, but it's certainly a topic for us at this meeting.
Yes, Dwight. And I just want to remind folks online, please either type in your question or raise your hand.
Hi, folks. Yeah, thanks, Dan. Dwight Cletto, NOAA's Ocean Acidification Program. So I love the idea. I love the vision of it. And I've been a proponent of trying to do, objective optimization of an observing system in the coastal system since we started over 10 years ago at the Ocean Acidification Program. What we find is a constant push-pull challenge. There tends to be a trade-off oftentimes between the scientific objectives and the user stakeholder groups that are asking for specific products, because the timescales of information products that they're looking to inform them don't necessarily coincide with optimizes what you're shooting for here, this big hack. So we need to find a way where this isn't a zero-sum game, whereby we can actually build an observing system that doesn't abandon the regional needs, right? But finds a way to repurpose much of that data and information in a way that achieves the climate information that we're seeking. Because I feel that much of the appropriations that fund these initiatives are often driven at constituencies at regional levels, and they're asking questions not at the national level, which I love to do as a geochemist, but they're asking questions about what specifically is the data information products and services that you'll be delivering to my constituencies. So maybe you could speak a little bit about who the intended users are of the climate signals you're looking for.
I'm just going to say what Jan just said, and we have to do both. I mean, we have to figure out a way to deliver on the immediate needs at the same time that we do the job that we need to observe the climate signal. I think unless we do both, I agree. I don't think it flies, but I think we can. I think in many of the regions they've demonstrated that it's certainly possible. I think the challenge from the regional level is to knit it together better at the national level. I think that's the challenge that we may face.
Thank you. I know there's other questions, but we're going to move on to our next speaker. And to talk with us next is Rob Campbell from Prince William Sound Science Center. Over to you, Rob.
Thanks, Jen. Yeah, I'm going to take you from the massive global to I think about as small as we're going to go. A bunch of hosers in coastal Alaska trying to keep an eye on things. My name's Rob Campbell. I'm an oceanographer at the Prince William Sound Science Center. I'm also acting CEO, chief scientist, vessel captain, chief engineer, head cook. You got to be versatile in Alaska, right? But I promise there's other people that work there. Yeah, so I lead the Prince William Sound component of Gulf Watch Alaska. That is a monitoring program that's supported by the Exxon Valdez Oil Spill Trustee Council. We do bog standard oceanographic monitoring temperature, salinity, nutrients, chlorophyll, plankton, stuff like that, vessel surveys several times a year. We also have a mooring we put out in the central part of Prince William Sound every year, and that's a profiling mooring. There we go. You got to have a cool acronym, right? I call it the Prince William Sound Autonomous Word Profiler. It's a big frame that we can hang instruments off of, all the stuff that we are using off the boat as well. It's battery powered, and it sits out in sound at about 60 meters depth, and then a couple times a day it will wake up and start paying out line. It's positively buoyant, and it'll measure all those oceanographic things. It's surface piercing. It'll connect into the cell site, send me a text, let me know that things are going well, send out some decimated data, and then pull itself back down to depth and go to sleep. And this is useful for us because it's nowhere near the surface, so it tends to not have problems with weather or getting run over. We do get that full profiler being surface piercing, and because it's quite large, it's about as tall as me, about a meter around, it can have a quite large payload. Being down away from the surface, nothing grows on it, and importantly, when things go wrong, it doesn't drift away on us. And it gives us a really impressive picture of what the surface oceanography is like in the Sound. And so this is the data that's been collected so far this year. We try to get it out in late winter before the productivity season starts. It does 2 profiles per day, the darkest time of night and the brightest time of day. And so what I'm showing here on the top is temperature, then the temperature anomaly, we'll get into that later, salinity, chlorophyll A, and then nitrate. So you can really see the productivity season happen. We like to call it almost godlike knowledge of what's happening over the growing season. We can see the spring bloom initiate in the spring, see all the nutrients get drawn down, and then moving into the summertime, we see a deep chlorophyll maximum sort of at the nutricline. Now, coastal Alaska is losing ice mass about as fast as anywhere in the world, as fast as Greenland, as fast as Antarctica. We also have something like 800 cubic kilometers of freshwater moving through the North Gulf every year, and that's also slowly increasing. And so there are some changes that are manifesting in the surface oceanography as a result of that. So when I first started working in the area, I went and put together all of the data that I could find, and I was able to put together a time series going back to the mid-70s. And it is kind of the story of interest in the area. In the late 70s into the early 80s, that was offshore oil and gas exploration time. So there was a lot of interest, a lot of waning interest in the 80s, until, of course, the Exxon Valdez oil spill happened in 1989. And there's been a lot more interest in watching what's happening there. So I have on the top temperature anomalies, then salinity anomaly, and on the bottom is the mixed layer depth. And that's estimated from the depth of the Brunt Vaisala frequency with quite a lot of smoothing. I think hopefully everybody here knows how dynamic and wiggly profiles are in the coastal ocean. And so you can see over time a warming trend. We have the blob anomaly. Yeah, I won't worry about it. Starting around 2013, 2014, in Prince William Sound, the anomalies really flip towards warm anomalies. We also see a freshening trend over time. And so that's manifesting as a decrease in the depth of the mixed layer. And so then the question is, what's that doing to the biology? Right. This also really nicely shows up in the temperature anomalies from that profiler. And so what I have here is all of the data we've collected so far. And you see the warm anomalies at the surface that we've been seeing recently, but the really big thing to notice here is the blue, the cool anomalies deeper down. And I've plotted the mixed layer depths with the little black dots there, and you can see it lines up with where those anomalies switch. And so what I interpret that is you can see the mixed layer depth is moving up, and so it's more deep water, which tends to be cooler, manifesting as that cool anomaly. So in terms of biology, the best time series we have for overall productivity is from the satellite record. We can go back about 25 years using CWIFs initially and then MODIS. They overlapped a bit, so we can compare. And so these are all the annual time series from that. And so just as a simple way of looking at how much green those satellites are seeing, I've just integrated all of the chlorophyll each year seen from the satellites. And you can see that we have a pretty big decline over the entire time series that we have. I wondered about changes in timing, so I've looked at various ways to diagnose when the bloom might be starting. This is just one of them, and there doesn't really seem to be any changes in the phenology of the bloom, but definitely less overall chlorophyll being observed. And again, my thinking on that was as the mixed layer depth thins, the overall amount of nitrate that's going to be available every year is also going to decline. As I mentioned, we also are measuring zooplankton. It's not as long of a time series, but we are seeing big changes in the species that we're seeing, which I noticed Dan mentioned as well. And so here I've put together, going back to 2009, the top is overall zooplankton abundance, and then some canonical cool water species, subarctic taxa, and then on the bottom, warm water species that are more common off of Washington and Oregon. And I'll point out on that top figure, the axis is, the scaling on the axis is a lot smaller. So we're not seeing super big changes in the total abundance of zooplankton, but over time we're seeing big shifts in what kind of zooplankton we're seeing there. And zooplankton is a little difficult because you have to go out with a net generally and collect it, bring it back, and look at it. So it takes a while to get that data. Oh, right, and then of course, this is cascading up to hydrotrophics, which I'm told we're not going to talk about at this meeting, so maybe I'll move on from that. But yeah, just to come back to that picture we have of the evolution of the surface layer over time. As I'd said, I'd initially been thinking that as we are getting a thinner and thinner mix layer, we're going to see less and less productivity as that gets squeezed. But it also occurs to me as that mixed layer gets thinner, the nitrocline is also going to move up a little bit higher. So there might be some other consequences of that, where that deep chlorophyll maximum might not be so deep anymore. So we might be actually seeing more productivity deeper down, which obviously be missed by the satellites. But for the rest of the talk, I thought I'd talk a little bit about the higher lower trophics. And what we're doing to try and keep an eye, better assess them. So in 2016, we developed a plankton camera with Jules Jaffe at Scripps that we put on the profiler. It just hangs out the side. There's a illumination on one side and a big telecentric lens on the other. And we get some pretty great pictures, just a few totally not cherry-picked ones. This is a Keating gnat and a small copepod who's probably about to have a bad day. This is a sea angel and its prey, Limacina pteropod, that's probably about to have a bad day. And this is a copepod and a big Balanopsis, ctenophore. I don't think that copepod's going to have a bad day, but we get quite good taxonomic information from just having the camera on the profiler. And when we dove into all of the millions of images we collected with the camera, we wound up with about 43 different classes. Everything from small copepods to large predators. And so we built a large training set and trained up a neural network classifier to identify these plankton automatically, because we collect far too many to identify manually. And so these are all of these classes, and the F1 score is basically accuracy success. And with a lot of classes, we get extremely good classification success. Things start falling down where there is more ambiguity, often things that people can't tell very well, the classifier won't as well. But we get upwards of 80–90% accuracy with a lot of the taxa groups. Just very quickly, I did compare this to a plankton net tow that we do every time that we surface the mooring, and they see somewhat similar things. I didn't make any slides for it, but the short answer is It underestimates things like copepods, which are very, very good mechanosensors and can probably detect the thing as it's coming up on them. But things like gelatinous plankton that get destroyed by the net, we see things in the camera that we actually never see in our nets. So pluses and minuses on both sides. But what's really interesting is we actually get observations of individual plankton, which tell us some potentially interesting things about them. This is distributions of Metridia. It's a copepod that does a really strong diel migration every day. And so I've broken it up. This is several years of data. And then I've broken it up into day profiles and night profiles. And so we really only see them at nighttime when they've undergone their migration. But when we have a picture, obviously the picture is time stamped to the millisecond. And we even retain where in each picture, each region of interest exists. So we can pinpoint where each of these individual plankters were to about an inch. And so we get a picture of where they're spending their time in the water column. And so on the right here in these nighttime profiles, each of these dots is an observation of one of these copepods. And so you can see there are clear differences from year to year. Sometimes we're seeing more, sometimes we're seeing less. You can also see this really interesting change in the depth distribution over the season. So behavior by these animals could be food, could be related to solar insolation. And so really the dream is to be using these camera-based estimates of zooplankton abundance. So we could be creating something like these annual cycles. These are made from actual data in Prince William Sound. You can see more high frequency variability from the camera. But ideally, we could be using the cameras to have more real-time observations of zooplankton abundance. And so is it big, hairy, ambitious goal? The maybe smaller, less hirsute, ambitious goal would be to have these near real-time observations that we can be passing on to our managers, because our economy is very closely tied to how many salmon come back, how many groundfish we catch. So there's a lot of interest in knowing about marine productivity, because often it's not really being incorporated into management decisions, fisheries management decisions. So the dream is to be able to say, hey, we're having a big zooplankton year, we're not having a big zooplankton year, and be giving that in near real time. And just to wrap up, where we're taking this, I've been showing you pictures of segmented plankton with the background removed, and there's actually quite a lot going on in the background as well. This is a copepod that's feeding in a patch of plankton. You can actually see its lipid sac, and the green line also in the middle of its body is its full gut. So there's actually physiological information in these images. And then moving forward, we're working towards a Pamper 2.0, second generation of the profiler. The one we have, and there's a few that's being used by OOI, are basically completely obsolete at this point. But for their purpose, they are extremely useful for watching one specific place. So our other BHAG is to have a profiler that is made with more off-the-shelf type stuff that can be built for something like 1/10 to the quarter of the cost of a glider. So you can watch more places or do it more cost effectively. In coastal Alaska, we're expecting big changes because of the loss of ice mass and regional warming. There are tidewater glaciers that are going to stop being tidewater glaciers in my remaining career, and I'd kind of like to be able to watch that happen more closely. And as well, real quickly, talking to a friend at Fish and Game about how they were aging salmon scales and how much work it was. I had her give me some scale images, and we just tried aging the salmon scales with the plankton classifier, and it turned out to be extremely good. It was 100% accurate with 1 freshwater and 2 ocean year sockeye salmon from Prince William Sound. So we're now modifying that plankton classifier and scanning lots and lots of salmon scales to see how well we can do and if we can actually apply this to aging salmon scales, which is another pretty important fishery in the region. And that's all I have for you.
Thank you so much, Rob. Okay, we're going to move on to our next speaker, who is Robert Todd from Woods Hole Oceanographic Institution. Take it away, Rob.
Thanks, Jan. So this short talk, I want to look at one particular climate signal that we've been able to detect fairly recently, and it makes use of a couple of different observing platforms, namely the glider operations I've been running on the East Coast, as well as Argo observations. So this is work with my postdoc, Alice Wren, who's somewhere in the room. So first of all, what have we been doing with gliders? So you've seen the map from Dan already. Now you can see a movie of gliders working in the Gulf Stream going back to 2004. Over that time, now there have been a total of 64 glider missions, most of those since 2015. You see in 2015, we accepted the fact that the Gulf Stream is fast and gliders are not. So we deploy in Miami, have the gliders cross the current while it brings them towards the north. Also, we've now completed more than 5,000 glider days at sea. That's something like 13 years at sea, over 38,000 profiles, and some 450 crossings of the Gulf Stream. And each of those crossings looks something like what you see at the bottom, where you see a section that's fairly high resolution, roughly 5 kilometers in the cross-stream direction of temperature, salinity. We have ADCPs on all of the gliders since 2015, and I'll talk about later what other instruments we're adding. So I'm going to back up a few steps then and look a little more detail at what our current observing system for the Gulf Stream looks like. You saw a snapshot from Dan of what it looked like in 2019, and some of the stuff in there has now come out of the water or shifted around. For these purposes, I'm going to focus on things that have timescales approaching or exceeding a decade, so really getting towards the climate scales. So first of all, the challenges in the Gulf Stream to observing. First, the currents are strong. That's a problem for basically any platform. It makes life rather difficult. So apparently there's timing on this slide that I didn't realize was there. There are sharp gradients. So that means you need fine scale measurements. But you need them over a large spatial domain because the Gulf Stream, so this is spanning something like 2,000 kilometers along the coast. So what are the components? So there are ships and moorings and cable-based observations that go back many decades, but they're at relatively few places. There's the cable across the Florida Straits and the ship cruises to check that. And then it's 1,500 kilometers downstream before the Oleander line and this XBT line. So there's a lot of Gulf Stream happening in between these wonderful, now 40+ year long time series. So a little over 20 years ago, of course, Argo came along. It has, as we've heard, been transformative. We all know that. Pardon my cursor that's moving around because this is used from a pre-recorded talk. So there are all the Argo observation locations over a 5-year period. So they do a really good job in the open ocean of filling in between these other fixed in location observations. But as we know, Argo is not designed to work in shallower water. So down here off the southern US coast, there are very few Argo observations because that water depth is less than 1,000 meters. So that's where the gliders come in. So now showing the same 5 years worth of glider observations in orange. There's about 3 times as many profiles. And they really fill in the Gulf Stream where even Argo doesn't get well because we're able to target their sampling. And then, of course, I'm not showing it, but there is remote sensing as well. Satellites are very important for observing the Gulf Stream, as well as at certain points along its course, shore-based radars also see the surface currents. So for this talk, I'll focus just on the Argo observations and the gliders. And ask the question is, how is the Gulf Stream changing as the climate warms? I'll start with what it's not doing. I hope you all know this loud and clear. The Gulf Stream is not going to shut down. Carl Wunsch settled this quite conclusively 20 years ago with a nice little, very short note to nature that as long as the earth spins and the wind blows, there will be a Gulf Stream. So it will not shut down. Please make sure you say that very clearly every time you talk to the media. That's not to say it's not changing. So the goal here is to use the 20+ years of profiles, particularly temperature and salinity from gliders and Argo, to first detect that what changes are happening, and then to understand and attribute what's causing those changes. So the plot at the bottom, the time series shows in orange the number of glider profiles on a monthly basis, and blue is Argo profiles on a monthly basis. So in recent years, the gliders really dominate because we can collect a lot more profiles in a shorter time, but Argo gives us that much longer reach back in time to 2001. And so the maps here are showing the subset of observations I'll consider. The orange glider plot, the glider profiles, in blue for the Argo profiles. So if we just take all the temperature profiles and look for a trend, so I'll show this as an example at 200 meters. Every gray dot there is one temperature measurement at 200 meters, just plotted as a function of time, and do a blind fitting of a line to that. Well, lo and behold, there is a trend. It's getting warmer, but it shouldn't be a trend line that makes anyone in this room very happy. First of all, it's not statistically significant. That's what the red bounds are. Second of all, the trend line doesn't go through any of the data. So that shouldn't make anyone very happy to use that trend as something to talk about. So why is that? Pretty simple. The Gulf Stream is a front. So there's warm water on one side, cold water on the other side. The observations in general fall on one side or the other. And you can see the observations cluster between the warm side and the cold side. So that's to say there's a lot of built-in spatial variability that's overwhelming any sort of slow, gradual temporal change that we're interested in here. So what can we do about that? Well, because we have a lot of very dense data from the gliders over the last 9 years now, we can actually build up a three-dimensional seasonal climatology. Essentially, it's just a weighted least squares fit to the observations. So when we have, with the climatology, then we can take our measured temperatures and we can decompose them into what we expect from the climatology at that place and time of year and the temperature anomalies. And so now, if instead of the raw temperature profiles, I give you a plot of all the temperature anomalies, both from the gliders and from Argo, now we still get a trend. It's actually the same trend that we saw before, but now we've taken out a lot of other variability. Our trend line is now quite statistically significant, and quite happily it goes through the data now because the data flaps down to wiggling about zero, basically. So at 200 meters, we're getting a trend of about 0.06 degrees per year of warming. So that's about 1 degree since 2001. And that's on par with what we generally expect as the warming has been over the last 2 decades. So the Gulf Stream's getting warmer. I hope that doesn't really surprise anyone, and it shouldn't be earth-shattering. I just showed you at 200 meters that it was warming at about 1 degree over 20 years. It turns out throughout the upper 1,000 meters of the water column, where we have the most data, we see statistically significant warming. So why are we seeing that warming? Well, obviously, we're pumping we as humans are doing a great job of making sure there's plenty more heat in the climate system. We all know the ocean's taking up a lot of that heat, so we expect the ocean to get warmer. So because we are measuring both temperature and salinity, we can do some tricks that are all detailed in the paper about this and work out how much of this warming that we're seeing is due to heat uptake. That's the red profile now. So near the surface, about half of this warming we see is due to heat added to the system. As you go below about 200 meters, it's very little of the signal. So the ocean is taking up heat. That's part of why it's getting warmer. It's not the whole signal. So what else is causing us to see warming in this region of the Gulf Stream? It goes back again to what I said, reminded you of before. The Gulf Stream is a front. So if we're essentially the temperature trends I'm showing you are essentially can be thought of as trends at particular locations. If you're measuring at one location, the trend you see in time can be due both to a local uptake of heat due to warming, it's the time rate of change here, but also a shifting of water mass, of temperature gradients. So this is a front. There is a temperature gradient. So by having the front move, the temperature at a given location can change. We all know about this from atmospheric fronts. When a front goes by your house, the temperature changes. It's not because the amount of heat in the global atmosphere suddenly changed. It's because you move through that gradient. So we're actually able to go through the data then and do another least squares fit based on the expected gradients across the Gulf Stream. And we can back out then that over this 20-year period, we've seen a shift of the Gulf Stream generally towards the US East Coast by about 6 kilometers per decade. So that means in the last 20 years or so, on average, over its extent along the East Coast, the Gulf Stream is some 10 kilometers closer to the coast. So this shift from towards the cooler side is something that climate models have long predicted. It's been a challenging thing to detect observationally, but now by combining two different observing networks, two different platforms, we're able to detect that signal that was expected to be found. So where are we going with this now? So we've been deploying gliders in the Gulf Stream now for the last 9 years, basically a glider going in the water every 2 months to resolve seasonality. Where we're going next, so there's a next generation gliders are coming online, and the plan is to take the opportunity that those new vehicles are going to offer to add new sensors and really build this up now from what it is now, the largely physics-based observing system with the gliders, to a fully physical and biogeochemical observing system. We already have oxygen and chlorophyll fluorescence on most of the gliders. We'll be adding sensors for pH and for nitrate in the next year or so. So in another several years, I can start telling you about climatologies and things of some of the BGC parameters. So stay tuned. I think we're going into break, but for the details of this are in a paper that we published in Nature Climate Change last year. It's also worth noting, but both the observations themselves are publicly available, and also that climatology that I talked about we made from the glider observations is publicly available. And that's it.
Thank you, Robert. We have time for one quick question, and then I'm going to throw the microphone over to the co-chair of the workshop and also my co-chair for this session, Nathalie. Is there a quick question? Okay, then over to you, Nathalie. Take us to the break.
Thank you, Jen. Can everyone hear me okay?
Yes, very well.
Okay, I just want to thank our speakers this morning and see. I'm really bummed that I couldn't be there in person, but visa timings don't always work for everyone. So I'm here virtually, but I'm really excited for this workshop. It's been a full, fun year of preparing this effort, and so I'm really excited to be here. And thank you so much to the participants in person and virtually. And I really hope that we can come up with some cool recommendations for optimizing the ocean observing systems. Thank you so much.
All right, thank you so much for coming back from the break on time. We're going to get started again with our final speaker for the session, and then we will have some time for discussion. So if you're online, make sure that you're typing your question in, or that you're prepared to raise your hand, and we'll call on you. And then we'll have some lightning poster presentations, and then we'll have some posters, we'll have some lunch, and then we'll come back for breakouts. All right, so it's a distinct pleasure and honor to introduce our next speaker, Harvey Seim, who is not only our next speaker from the University of North Carolina at Chapel Hill, but he's also a friend who I've known since before IOOC. Harvey, over to you.
Thank you, Jan. And yeah, it's exciting to be here. And I was given this wacky charge of talking about challenges and opportunities for the coming decade. And I wasn't on the steering committee, so pardon me, I have some higher trophic level things mentioned in my slides. But I think they're important to know about. So I'm just thinking about the challenges that we've heard about this. And I think one of the challenges for me was trying not to be agnostic in terms of parts of the US that we're talking about. But we're confronted with changing oceans, atmosphere, cryosphere. I think that's really important to remember. We cover that much of the globe. And they have a wide range, these variations, crazy range of time and space scales. From hurricanes, tropical cyclones, to warm blobs, to decadal shifts in temperatures. And the impacts are broad. They're physical, biogeochemical, ecological, and societal. I think the social changes, the social systems piece of this, we really have had to keep in mind as part of IOOC. It's a critical aspect of this, that coupling to the communities at the coast. And I think one of the other things that we all know, that the coupled system that we're trying to observe is badly undersampled. I think we We do a reasonable job, maybe of measuring surface temperature. Beyond that, it's not clear to me that we do a good job with much else. Satellites play such an enormous role there. We have beautiful point measurements at certain places, but in terms of geographic scope of what we're talking about, it's really badly undersampled. And one of the things that's key, I think, for the coastal ocean systems is the benthic side. What's going on near the bottom? How well are we monitoring those changes different from what's happening at the surface? Systems of interest we're interested in across many disciplinary boundaries. And again, I want to emphasize that the social science connection. We're trying to think about how we connect back to communities at the coastline and the impacts on their lives. And so that's an aspect, at least for me. I'm a natural scientist. That's a tough one for me to think about bridging those boundaries and how we do it. The systems of interest, these things we're looking at, they're increasingly non-stationary, right? We're seeing extremes that are outside of what we thought we would have seen. They're shifting baselines. Even identifying what we're talking about can be challenging in the face of these kind of non-stationary statistics. It challenges our ways of conceiving of what constitutes an anomaly. And I wonder about how well we're going to deal with this. I think what happens a lot is we hear about catastrophic events. And here's my example. So here's the slide shows on the right the collapse of the eastern Bering Sea snow crabs, right? And I think we were caught off guard. Didn't know that was coming. Had a hard time even putting back together what had gone on. Right, granted it's higher trophic levels, but it's kind of an indicator of just how badly we're sampling things, I think, that we didn't see this coming. So those are among the challenges. The other thing I was told about, that the footprint here is out to the EEZ. That's an enormous territory we're thinking about covering, and we got to use the breadth of observing assets at our disposal. We heard a lot about these this morning already, fixed, mobile platforms. Just an amazing proliferation, I'll point out, in mobile platforms that we've seen. I guess I'm thinking more about the sail drones and wave gliders and animal tags that have just been coming online more and really augmenting the data sets that we have available to us and new and novel ways of observing the ocean. Remote sensing hasn't gotten a lot of attention yet, but I think those satellite systems are of critical importance. One of the ones I think that's very exciting for me as a physical oceanographer, SWATs. Up there, it's online. We're starting to see what the mesoscale activity is like in the world's oceans, like we never have before. We have a reasonable sense of what that's like in the deep ocean. We don't have much of any sense of what that's like in the coastal ocean. So it's a great opportunity there. PACE, hyperspectral sensor. The hope of getting at community composition. Again, I think that, well, even there, I think open ocean and coastal systems really need lots of help with that. Coastal remote sensing, I'm thinking here of the high frequency radars, but also offshore platforms. The wind industry is coming. And I think that's going to be a challenge for us, but also an opportunity. There's a lot of new platforms out there that we may be able to leverage. Point out that later. We have a whole host of agencies who are now participating in monitoring. George may be a little distressed that I have OOI listed up here, but they're collecting continuous time series that span now 5-10 years. That's important. That's new data, in addition to what NOAA and IOOs and USGS and EPA have been doing for years. There's the process studies. They got highlighted in some of the slides before. Some of the bigger ones have really helped augment our existing database. And I think we need to be, again, utilizing anything we can, but those that are funded by the various federal agencies. And I think a key thing, again, that we need to remember is measures of human activity and use in the coastal ocean. I think that's increasingly important for us to be able to track that. And it goes back to something Robert talked about, which was attribution. I'll mention that later. These are all platforms. Some of them are variable specific, but there's a host of things to measure. I think Rob did a wonderful job of highlighting just the collection of things you need just to start to put the story together. And it's those measurements of the biogeochemistry and the multiple trophic levels that have challenged us for so long. And that we're seeing some real progress with. I think the imaging systems that are now coming online that can be sustained out in situ deployments for weeks, months, is really going to advance our ability to measure, especially those lower trophic levels. And something hasn't gotten a lot of say yet is modeling. And I think it's critical for us to have a large suite of modeling systems because we're so badly undersampled. And we need models of all sorts of types. And they're needed to interpolate the information spatially at the time. But the other thing they enable is once we have those gridded fields, it gives us access to these statistical tools which are so powerful. So that's how we're able to analyze and identify the complex connections between physical and biological variables, for example. The other thing they could do is help us identify where the uncertainties are greatest. And I just list a few of those types of modeling systems that I'm thinking about and familiar with. We've seen just remarkable advances in nowcast and forecast systems. Let's see if we can push them down to a regional scale. Lots of ways to do that: nesting, downscaling. Reanalysis products, there were some, again, just remarkable advancements here, but they tend to be at the global scale. We're starting to see some of these reanalysis products develop for the regional systems. Maybe that's something we should really be pushing on to see if we can have integrated depictions of the information we've collected over the last 20, 30, 40 years through these kind of reanalysis products. A few groups are running coupled nutrient, phytoplankton, zooplankton, detrital kind of models that trying to get at the biogeochemistry. Again, essential, the validation data we have for them is so varied across the footprint that we're looking at. Ecosystem models, again, just take it up above those lower trophic levels. But that's where a lot of the human interest is. That's where a lot of the connections are to the coastal communities. I don't think we can ignore those. And just as an example of the variety of models I'm talking about, just correlative distribution models have advanced our understanding. And I've highlighted here a recent study by Welsh et al. That looked at the impact of marine heat waves on top predator distributions along the west coast of the US. That's what these graphics are showing. Just so some depictions of the blobs that have happened over recent years, but also what are the distributions of those marine predators along the west coast, and how do they correlate with these blobs, and then what are the impacts that they have. So I think there's tremendous amount of value in exercising our understanding through the use of models, and they can help us evaluate the impact of new observations and think about where new resources need to be applied. And also I think they can play a critical role in attribution. So this is something Robert talked about. Just as this room, it's not anything new. I think we all want to understand why something happened. But I think it's going to be increasingly important. These are the things that are getting into the press. These are the things that are getting people excited about climate changes. Why did that happen? Why are the whales all washing up on the coast? Why did the scallops go away? What happened to the crabs? And we really need to be able to provide those kind of answers, distinguishing large-scale climate variations from more local effects. The wind industry is going to, again, I think this is something that's going to really push this topic. And it's happening in the fishing community as well, as they watch various aspects of the fisheries that have been so sustainable and predictable for some, in cases, hundreds of years. And they're changing so rapidly right now. Just a thought on my side, spatial and temporal scares that the variation are likely major clues in this game, but it also means we'd have to have observations dense enough to be able to make those kind of conclusions. And I don't mean to say that the models are the only way to do this. Just straightforward, simple analyses along the lines of what Robert told us about can also be what we use to make these, to arrive at these answers. And what's shown here is a recent paper looking at the collapse of the sea scallops along the Mid-Atlantic bight. And what did? They concluded that it was warming and fishing that were impacting the distribution changes that we were seeing, but ultimately that the temperature changes that are coming are really going to shift the species distribution a tremendous amount. And that's what's shown here is as bottom temperatures are increasing, that the scallop fishery is going to be shifting north many degrees of latitude. I think that we need to really leverage opportunities for more resources. We have been playing this game for 25 years or more, trying to figure out how to build out our observing system in a thoughtful way. But there seems to be a new alignment of interests, and I think I was really heartened to see what the participation is in this workshop, and we really should think about how we can help coordinate these funders of climate studies, and that was really highlighted for us in the documentation that we got in advance. I think we also need to think about partnerships with maritime industries, shipping and fishing. Been thinking about it for a long time. I think there's more receptivity there as things start to become so wild, especially for the fishing industry. I think they're really maybe wondering what else can be done. How can they help? I'll say it again, renewable energy studies. I think there's such a focus on this, at least in my part of the planet. I think it's happening around the country, or at least in a number of the parts of the EEZ we're talking about. There's going to be a lot of resources that are going in there. They're going to be confronted with these questions of attribution. We need to push them on data sharing and cooperation and collaboration. And once they're up and running, there's going to be a need for monitoring. And there could be a real big infusion of resources in support of that. Vessels of opportunity, we've been working on this for years, both commercial and recreational. Certainly worth doing. Citizen science, it's really come to the fore, I think, in the last 10 years, especially in the near shore, as a way to help us have more information. And I think we can think of more, but that's as far as I got. I think there's some key actions we really need to think about. And one, I think, talked with Jan about this a little bit before, streamlining and incentivizing data sharing. It's been a long-term thing, but there's just a tremendous amount of information out there, but it's still hard as hell to get at. We can do better. And that data sharing, I said writ large there because, again, I think it's the social sciences information coupled with our natural sciences data that's going to be so important as we think about attribution going forward. And if we can share those data, and people are great data miners. We have individuals who are expert at this, but I think reviewing these existing observations and existing observational plans is really important. We have been thinking about this for 20+ years. There are a lot of really nice observational plans out there that were funded at 10% of the envisioned level. So there is some consistent and thoughtful designs out there. They've never been built. Is there an opportunity to review those, think about what we might change, how we might better coordinate them that we can think about? When you look at them, it's clear there's crazily wide variations geographically. We have very different concerns as we move around the country and across the EEZ for the US. And that has to be recognized and incorporated in whatever we build. And that really figures into this, what kind of investment we want and which essential variables that we deem underreported and which are critical. Hopefully we can identify a handful that are common, but there's still going to be a need to tailor that for specific geographic regions, what's going to be most important in a given area. And critical in this, I think we have a lot of existing knowledge. We really do, and that's factored into the existing designs that we've got out there. Continue to use it, we're always learning more. And of course, the modeling systems can help us optimize. Talked about OSEs and OSSEs for many years, and they can really help us in fine tuning, but I think it's our innate knowledge that we've accumulated over the years that's really going to help us get there. Probably would be very fast, but I'll mention one kind of harebrained thought. Many years ago, I worked a fair amount with a guy named Chris Moores, who some of you may recall. Interesting character, brilliant man. And he had a vision at the time, and he really wanted us to think about planting seeds in the National Weather Services field offices to be ocean forecasters. And we thought it was a cute idea. Never happened. But I wonder about this. I really think that there's a great value in the role those people play in the weather service community, right? They're looking at the data all the time. They're looking at the models all the time. They're comparing them. They're trying to understand where the models are deficient, developing local knowledge. And I think that will push us towards that goal. It's just a thought, as I said, that if we had staff that were dedicated to their day was spent analyzing ocean data in their region, they're gonna force themselves and us to share the data. They're gonna be looking at it, finding what's good and bad, help us highlight where the observations are lacking and where the uncertainties are large, and help us tailor those things. So I think it's a thought. And what would be different, I think, from what Chris envisioned is we're not going to plant a bunch of people in the field offices of the National Weather Service, but maybe there's a way for us to connect people with similar interests across the various organizations. We have a really big range of time scales and space scales. As I said, that people are interested in. Different organizations have different foci, but maybe this can be a rallying point. But I think we need to find something like that. So just as a summary, our coastal settings require geographically tailored transdisciplinary approaches to assessing climate variability. And we need to use all the tools at our disposal. We're going to think about improving our observing systems, spinning up more consistent modeling systems. Think about the applications that come out of that. What advice are we providing? The coordination across the funding organizations, the organizing missions they have can be so different. I think what we really need to find is some unifying activities. So my simple idea about ocean forecasters. And lastly, I think and this was highlighted in some of the documents that were shared for us, the application of our understanding for safety of coastal communities, their health, their resilience, so the mitigative strategies we might take, they really need to be integrated across impacts. We need to think not only about the short term and the long term, but together, what's the right approach to addressing these problems? And I think that requires a new level of synthesis that we probably haven't gotten to yet.
Thank you so much, Harvey. That was really excellent. So we have just had 4 speakers, a real tour de force, Dan giving us the perspective of how we've gotten to where we've gotten to. We heard from amazing observing in both the Pacific and the Atlantic and how powerful that can be. And now Harvey with challenges and opportunities. So I'm sure you have questions. So now is the time, online people and people in the room. If you're interested, raise your hand and come to a microphone. If you're in the room, raise your hand and I'll call on you if you're online. So Dylan.
Thanks for all the awesome talks this morning. Harvey, I just wanted to follow up on your old idea that might see its day. This is actually happening within NOAA right now. If anybody's familiar with the Climate Ecosystems Fishery Initiative, or CEFI, and maybe I'll just summarize it quickly for the folks in the room that aren't familiar with it. It's a pot of money that NOAA was given recently to basically bring operational forecasting up to speed, try to get it on the same plane as national weather forecasting. As far as I understand it, there's not funds or FTEs in place to hire, the dedicated ocean forecaster of the day, similar to what we have in the National Weather Service, but there are operational regional ocean forecasts down to 10 kilometers or so, maybe to 1/25th degree in certain regions that are being developed right now at NOAA labs. And the plan is to have those roll out in the next few years with making that, the plan is to have those models roll out in the next few years and make that data operationally available to users through a web portal that's also being currently developed. So anyway, I just want to say that that old idea is seeing its day now. And at this point, we just need the user base to justify, the continued support for maintaining those models operationally going forward. But it all is all in the works.
Yeah, and thank you. And I guess I am aware that it's starting. And I think it's the right direction, and that maybe this is another place that we can think about investment across the various organizations represented here. As I said, some kind of a unifying activity, because I think NOAA's focus, I believe it's on large marine ecosystems largely, right? And that's maybe not the breadth of topics we need to engage in. So that's great, but how can we augment that? How can we build a stronger core of folks that are working on that cuts across a larger suite of topics that are of importance?
And I'll just add, Dylan, that's great to hear. And when I introduced myself, I said I'm from the University of Washington, which is true, but I'm also the director of NANUS. And I would love to know who our CEFI person is in the Pacific Northwest and how to better integrate. It's you, Michelle? Perfect, perfect. And so this is exactly what Harvey's saying, getting these synergies to come to bear. So thank you. Shut up now. Come on, don't be bashful. Other questions? Yes. Glenn.
Workowitz, Woodsville Oceanographic Institution. Wonderful talks this morning, very, very stimulating. And Harvey, I really like the idea of the regional forecast offices as well, because it could be a national scope. So I have a question about resources. And that is there any role for philanthropy there? Philanthropy tends to be very individual, institution oriented there, and we're trying to integrate here across national needs. And I'm just curious for all the panelists, if there's any thought, if there can be consensus out of this about reaching philanthropy on a kind of a deeper, bigger level there, as any Lego dad would probably suggest.
I like it, but I'm not sure how to approach it.
Yeah.
I think that's been a tough nut to crack even at the institutional level. And as you said, very specific. So I'm not sure who we have do the pitch and where those resources would lie to make sure that they provide truly national coverage. Maybe that's some of the things to think about in that regard.
Yes, but we also have somebody online. So I'm going to go to Patrick Barnard. Do you want to make your microphone come on and read? Otherwise, I can read what you've written here. Patrick? Okay, Patrick says, how do we define the landward margin of the coastal ocean? I'm going to say that from the IOOC's perspective, it's head of tide. I think there's probably other things out there. He says, I think I have heard the shoreline. If so, that boundary is extremely dynamic and varies due to short and long-term drivers, including tides, storms, waves, and storm surge and sea level, all of which have implications for people and infrastructure at the coast. I don't expect CLIVAR and the USAs to get into the coastal hazards game, but they can track that coastal boundary via satellite observations and use existing network to track changes in the energy hitting that boundary, such as waves and water levels. Do you see this as an opportunity or niche for this group? And that came from Patrick Barnard of USGS. I will say that from the perspective of the Integrated Ocean Observing System and through the Inflation Reduction Act funds, we have some pan-regional effort on waves and water levels. In fact, Deborah Hernandez, director of Socorro, is leading the water level or webcam portion of that. There's waves, water levels, and webcams. So there is some good effort on that. Deborah, I don't know if you want to say anything further. Yes, I want you to.
So yes, I do think it's a challenge. The mismatch of where all the people are and the definition of what the coastal observing system is. Because I heard Robert say earlier the shoreline, and for me that means out. It doesn't mean up into the watersheds where most of the people are. But the programs that Jan just highlighted involve putting lower cost sensors right in communities to measure various coastal phenomena, shoreline change, water level rise, sea level rise, et cetera. And there's just a huge demand signal for that, and figuring out how to integrate that on the land coastal piece with what we need to know and understand as we move offshore, I think is one of the challenges that maybe won't be addressed here, but that the IOOC regional associations are trying to address.
Thank you so much, Deborah. So Ed, I'm coming to you next. Then I'm going to come back to online. Adrian Sutton has a question about data integration. Then I saw Dick Feely. So Ed, over to you.
Thank you, Ed Dever at Oregon State University here. I guess, one of the questions, I think it touches both on Harvey's talk, but also spurred a little bit by Dan's talk earlier this morning. When I think about optimizing ocean observing networks, I thought, probably like many of the people in the room, about how do we knit together regional networks? And what I really hadn't been thinking consciously of until this morning, when Dan talked about it, are platform-based observing networks. What's the relative efficiency of those different types of networks? And, I think about, well, yeah, GLOS, Argo flows, HF radar, they're pretty effective at distributing the data across to a large number of users versus, I'll take my own project that I'm involved with, OI. We've got a huge number of different types of sensors all reporting by different means, and it's a real challenge to put the data out to the appropriate user community. So as we're thinking about optimizing these networks, are we primarily thinking about the regional networks, or are we thinking, maybe about building networks based on platforms?
Yeah, thanks, Ed. I mean, I'm glad that got you thinking about this issue, because that was my intention. It's an accident of history. Maybe it makes perfect sense, but the global system is largely platform-based. It just is. I mean, not to put any value judgments on it, that's what it is. And the coastal system that we have through IOOC is largely regionally based. And not to put value judgment, but that's what it is. And maybe we can think about this and decide of these approaches, which seem kind of orthogonal to me. How do we make something good out of all this? That's a great question.
And I think I'd just add that there is no one platform that can do everything we need. So in the sense of building a comprehensive climate observing network, be it coastal or global scale, we have to use these complementary platforms. They all sample in very complementary ways. They sample different things. So that we have to keep that in mind, even if whether we end up planning with a focus on the particular problem in building the network or focused on individual platforms. We have to look at how they work together.
And I'll just say a little bit that the regional observing system designs tried to use multiple platforms. And there are a lot of plans out there that have a variety of platforms that are included. The degree to which they ever got funded is variable. I think the platform-based approach is very attractive because it makes life so much simpler, especially with the data management. And that's largely how our data management systems are organized, or by the platform. It's relatively straightforward to integrate by platform. That's not what we need for the science. I think it needs to be cross-platform by variable somehow. And I think we're still struggling to get there. But that seems to be critically important in terms of the data integration, to break from, at least at the data integration side, from this platform-centric kind of approach.
Hey, next, Adrian Sutton, if you could undo your mic and start your video, please ask your question about data integration. Adrian.
Yeah, I was thinking along the same lines that the panelists were just getting at there. I think that there's a lot of low-hanging fruit on the data integration side, not just across platforms, but I think also across EOVs. We have in detecting climate signals, it is inherently multidisciplinary, and a user needs access to data that are integrated to most easily do that. And so do the stakeholders. And so I'm just wondering what the panelists think about that. And, I just want to also throw out there that, I'm glad Dan brought up the IOOC and Goose differences this morning, and Goose is in the process of re-envisioning Ocean Ops, which is their primarily metadata platform. And now would be good timing to come to them with recommendations and maybe have easier way to integrate across, those regional networks and that global network.
And I guess I'll start with, and sort of building on what we already said, that we have particularly the global scale, we have these DACs by platform typically that gather the data. And it seems like the time is getting ripe to have a layer above those that then takes where's the temperature global assembly center or something that takes all the temperature data from Argo, from gliders, from everything else that's out there feeding out data and puts it all in one place. I think that's a big project to do, but it would probably be supremely useful.
I'm just going to add in that to me, one of the things that came out of the Ocean Obs is the FOO, the Framework for Ocean Observing. And what that said is that observations should be based on a need for data for a purpose, right? And I think that should guide, regardless of whether it's a regional scale or a global scale, we should really be keeping that in mind and thinking, and honestly, I think our glass is more half full on that purpose in terms of how things got designed, but I think our glass is more half empty on how we're sharing and integrating that information. So I see that as a real difference. All right, Richard, over to you, and then to Seth.
It's been a wonderful discussion today, and I really appreciated all the comments that were made by the panelists. One of the topics that came up was briefly discussed by Dan and others was the concept of long-term climate change and how you measure that as opposed to climate variability, which is on a different temporal scale. Now, those of us who work in the open ocean have been struggling with this for many, many years and have developed some tools and approaches by combining observations and model to address the long-term climate change, utilizing the models to extend back in time that we can't get from observations. I'm wondering if we are going to be thinking about today about how we might integrate the observational system to be able to address both the long-term climate change as well as the climate variability. I think both are really quite important. For ocean acidification, the long-term climate change is a major issue for us. So if we think a little bit about how we would address it in terms of our approaches, I think that'd be very worthwhile part of the discussion.
Yeah, I think this is a great comment. I think it's at the core to do, and I think we clearly want to do both. I don't think there's any question about that. One of the issues it brings up in my mind is it really does bring up the issue of accuracy. Some of the climate fluctuations, the variability, if you will, like El Nino, they're pretty big. And it's not as hard to measure that as it is to measure the longer term changes. And I do think we have to really consider on a broad basis how accurate we need to be for those two kinds of variability. I think it's very important.
I think another thing that it brings up in my mind is just how precious time series are and preserving long-term time series. In a lot of cases, and I can cite Pacific Northwest examples, but I won't, these assets were cited for scientific reasons as well as for stakeholder, tribes and state agencies wanting something. But a time series has been established that now can also help us not only look at climate variability, but also climate change. So I think it's really critical. Who was it? Francisco Chavez said, never stop a time series, but never start a time series. Because once you do, you realize how powerful that is and that it will need care and feeding, but the payoff is so extreme. Over to you, Seth.
Yeah, thanks for a whole bunch of really nice talks this morning, thought-provoking. I want to make the point that a lot of the the measurements that we're starting to make now are really still based on emerging technologies, and that there's, I feel like there's a key need for some sort of collaboration amongst the regions and amongst the researchers. Rob, you've got that amazing thing taking pictures in Prince William Sound, and version 2 is coming out. Figuring out ways that you can work with people around the country to standardize some of this so that right now the DACs, we have DACs for some of the data, but some of the data that we're collecting on gliders and moorings have no home in the DACs. And so we need places for the data to go. And I guess looking at the data and applying some of the new technologies, artificial intelligence, to extracting the most useful information out of this data are all things that are ripe for organizing around. And yeah, maybe we can make some motion on this this workshop towards making a plan.
Yeah, it's true. On the image classification side, one thing I've learned is if you have a training set, then you start getting emails from the AI community because they're so hungry for that information, and there isn't a central clearinghouse for it. In part because, yeah, everybody's doing their own separate thing. At Pisces, there's a working group specifically on plankton imaging where we're kind of wrestling with that and trying to come up with some standardized ways to store things.
So I keep seeing hands here, but that's because you're in my field of vision and I can't see over here. Are there any hands over there? Dwight, and then, I'm sorry, I'm spacing. Jen, yes, okay, you're next. And Deborah.
Deborah was before me. Sorry. I'm going back to the statement about why it is maybe we have these disparate approaches between the open ocean, which is very platform based, versus the coastal system. And it just, just reinforced me of this idea that in some ways it's a little naive the way we approach this topic. We're like, oh, we've got a fantastic global ocean observing system, of which is incomplete. And so we're just going to do coastal system. It's a totally different ballgame. I mean, I get to sit here next to David, and I'm always jealous because he does a lot of his geochemistry out in the open ocean. And our program is heavily focused in on the coastal large marine ecosystems. We're not monitoring the ocean. We're monitoring a reactive boundary. It's a totally different system. Material flux, chemical fluxes, interfaces, land, sea, benthic ocean, all of that is playing out in the system. So hold on tight, because if you feel we don't have the coverage necessary to do an open ocean, hang on, because there's a hell of a lot happening in this system that needs to be characterized. And to date, there isn't a single technology that's at least been presented to our office that managed the coverage at the data qualities that we're after in most of these systems, particularly in the subsurface where everything is happening. So it doesn't surprise me that there's this balkanization across the various regions, because this is a reactive interface that you're looking to measure. It's like a different ballgame. So.
Thank you, Dwight. Okay, I'm going to take 2 more questions. I've been told I need to cut this off. So Jen and Deborah, you had your hands up. If you can go to the mics and be ready, we're good.
I'm Jen McWhorter from NOAA's Atlantic Oceanographic and Meteorological Laboratory. And I just wanted to make a plug for climate extremes. And I don't think that's kind of come up yet in conversation. And maybe starting with users that are facing health risks and death as like an immediate need for ocean observations. At AOML, we forecast hurricanes, and a lot of ocean observations are going into those forecasts. So things like that, heat waves, harmful algal blooms that can cause poisoning and whatnot. I think, that's worth a lot of discussion that maybe hasn't come up yet. So thanks.
Thank you, Jen, for that comment. Deborah.
Thanks, Jan. Thanks, panel. My question is about the term optimizing, and some of you tried to look across what we already have. moving forward to optimize, is it about rejiggering what we're already doing, to use that very scientific term? Is it about filling major gaps? Because it's obvious that are huge gaps. Is it about not doing anything? And please don't say all of the above, because optimizing means we're going to prioritize in some way, in my mind.
Yeah, I think the first step in optimizing is deciding what your objectives are. And, you know, that's a hard discussion because that is going to guide what you'd want to optimize. So I do think that what you said is correct. Step one is deciding what are our objectives? What are the scientific objectives? What are our objectives towards helping society? What do we want to really accomplish with this? And then once you have objectives, there are a lot of approaches to optimizing. You know, everybody has their Aussies, but we really have to decide what we want to accomplish first.
Okay, live, is it really quick? Come to a microphone. I'm going to get yanked off the stage, but for you, I'll do it.
I just had a couple of thoughts about the optimization. It was a big part of what Dan said. And in terms of the priorities, I think we saw some of them, the things that are common across the region: harmful algal blooms, ocean acidification, sea level rise. And so that could be a focal point to kind of limit our scope to think about optimization. There are probably a lot of tools for it. I would advocate strongly for reanalysis integrated data products, but they're modeling and other approaches. So thanks.
Thanks, Lad. Okay, I would like to call for one more round of applause for our speakers this morning. And thank you so much for the audience participation. I'm really excited to get to our breakouts so we can discuss more. So I'm going to turn the baton over to Alyssa, who will introduce our lightning talks for the virtual posters. So we're going to hear from the authors of these lightning talks. Come on up, who have only 3 minutes to present. And so please stay on time. And Alyssa's going to take us through this.
Our first presenter is Kisei.
Okay, great. Good morning. I'm just calling in from Hawaii. I'm based in Hawaii, and we have a lot of islands, a lot of temperature analysis we need to run around coastal water around islands. And we've been using this high resolution 5 kilometer SSD product coming out from NOAA. So another topic of discussion that we've been having is the detecting the extreme heat event around island waters. So we've been using this high resolution SSD product, and every grid cells and every month we are able to detect the signals that goes above the baselines for each month and each grid, and we are able to calculate the fraction and area fraction of this extreme heat event or annual fraction of this heat event, and we've been able to understand the high resolution gradients of how this temperature have been shifting out of the historical bounds, even at the island scales. So I'm only able to show the just a fraction results on the right-hand side, that we are seeing that the west side of Big Island, Hawaii, has been seeing the large divergence from historical baselines. And then we work a lot with coral reef scientists, and we are able to compare the large-scale heat signals to conventional metrics such as degree heating weeks or bleaching alerts. And then we are seeing interesting results and hoping to put this in paper probably next year. Thank you.
Thank you so much. Next, we have Adrian.
Okay, so in this slide, I'm sharing 2 tools to help detect climate signals: a best practices paper for assessing trends in surface ocean carbonate time series and the associated code for doing that. So in the best practices, we expanded techniques from several published trend analyses and packaged them together with a focus on ocean acidification. But these techniques can be used for monthly resolved data sets where seasonality is the dominant signal and monthly anomalies are used to assess trends. We packaged all of those into open source software called TOTES. that computes and reports trends. It's Python based, but you don't have to be an expert to use it. People new to Python have found it easy to use. One of the goals for developing TOTES was to expand the community of practice doing ocean acidification trend analyses. So making it easy using open source software was a priority. Now, on the next slide, I'll show some output looking at trends across the ocean to coastal interface. But if anyone has questions about using the software or whether these techniques could apply to certain data sets, please reach out. My email's right there. Next slide. So there are 2 buoys located off the Southern California coast that provide a link between large-scale open ocean climate variability and its signature along the coast. That's CCE2 on the coastal shelf off Point Conception, and CCE1 offshore, that's within the Southern California current. So on these buoys, we measure 3-hourly surface ocean PCO2, which I have used to calculate aragonite saturation state. If you could hit next. And we find a significant trend at the offshore site that's consistent with the global average trend driven by ocean uptake of increasing atmospheric CO2. So that's that figure at the bottom. It shows the original observations in blue, monthly means in black, and the monthly anomalies in red that are used for the linear regression. So that figure and the summary that I'm showing on the right is an output of TOTES. So you can see here that the significance of the slope coefficient, the R-square value, the trend in trend uncertainty, and the trend detection time in years based on the signal to noise ratio. And so near shore, which is at the top, we don't find a significant trend. Note that these y-axes have different ranges. So you have a seasonal range of 2 at CCE2, but only about 0.5 at CCE1. So at CCE2, the time series length is about half the time needed to detect a long-term signal above the noise. And you can see the other statistics there. So it'll take a little bit longer or better constraint of coastal variability to detect a trend at that site. Thank you.
Thank you so much. Next, we have Yolanda.
Thank you. Yeah, my name is Yolanda Sarah. I'm here in Seattle at the University of Washington's Cooperative Institute, and I am working with Megan Cronin, also here in Seattle, and Dongxiao Zhang, and we have a co-I at the NDBC, Ian Sears, and these are our other colleagues that are helping us with this project. It's the point of the project is a pilot upgrade, we call it, of the NDBC coastal weather buoys. We're working with 1 buoy at the moment for improved monitoring and of weather and climate. This project is funded by the Weather Program Office, and it's a 2-year project, but we had some slow getting started. We had some personnel changes and so forth. So we're kind of behind by a year. So I'm not going to be able to show you any data. The mooring is going to go in the spring, but I'm going to just talk about the project. Next slide, please. So this is a map of where it is. We've chosen the 44008 site after some discussion with various people that work in the region. 44066 and 44011 are also on the shelf, New England shelf, or in the Banks area. We found, I think there's most value for this first project to try to work in the area of the OOI Pioneer New England Shelf Array that was just taken out recently in order to move it further south off of the North Carolina coast, which I'm sure all you guys are mostly familiar with. So we are hoping to add value to what had been collected more intensively in this area. So the idea of the mooring is to make it full flux. So all air-sea fluxes all the components of the air-sea fluxes, including net shortwave and long-wave radiation. So we're adding those sensors, upper ocean mixed layer information in this Gulf Stream frontal region. So the output would be the prototype coastal weather buoy with subsurface temperatures and salinities and currents from an ADCP, and then surface radiation oh, this should be sea surface salinity. They already measure sea surface temperature. I think that got, maybe it's an older version. And then this is the setup here. I don't know how well you can see this, but the ADCP is an upward looking, installed at about 55 meters. And then the temperature conductivity, and some pressure sensors along the mooring line with a surface current sensor, and then the added conductivity sensor here with the SST, and then the added radiation on the top side. And of course, they already provide surface met and wave height and frequency and so forth information. Next slide, please. So this is a movie, again, I'm sure you guys are very familiar with the variability in this region. The Gulf Stream comes through here. It has strong seasonal and interannual variability. The stars representing roughly the location of this prototype mooring. I think it's interesting to point out that there are 104 of these platforms out there in the coastal regions, and there are 33 along the US East Coast and Gulf of Mexico, an area with tropical storms and hurricanes that track through the region. Extratropical transition can occur here, as we saw with Hurricane Sandy and so forth. And there are evident climate change signals, which we've heard about this morning. So this was just we call it the pilot because it's just an interesting idea to kind of integrate the NDBC platform into this coastal observing system and understand how we might optimize these platforms as well and maybe add to them. So that's all I'll say. Please visit the poster and see more about the project. Thank you.
Thank you. Next, we have James.
All right. Thanks for having me. Thanks for extending a virtual attendance option as well. It's much appreciated. Hello, folks. I'm James Behrens, the program manager for CDIP. I believe many of you would already be at least somewhat familiar with CDIP. We are in part a national wave observing array focused on using data well wave riders. Here's the poster, and then so I'll just take you around the poster. Down on the bottom left there is an indication of some of the data streams. We have directional spectra, and we also have climate signal going back nearly 50 years. This program was founded in the 1970s, and over there on the top right, it shows the history of our platforms. We're very much a platform-based program with primary funding from the Army Corps of Engineers. And the platform in the early days was the pressure sensor, the 4 pressure sensor array to get the wave direction. And over the decades, things have gone from old-fashioned tape and printed data to now we have the new Mark IV data well system that measures the surface currents, the sea surface temperature, the air temperature, as well as the directional wave information. And we are producing a coastal wave model for California, focused on the investment from the California State Parks. That's over there in the top right. We've got a nowcast as well as a forecast, and that has become operational with partnerships at the Port of Long Beach. We issue not only these plots over on the left that indicate the climate signal at all these various observing sites, which is approaching 100 in US waters worldwide, from the Western Pacific to the mainland coasts, Alaska, the Great Lakes. And when we measure extreme events that stand out from the climate record or that have particular coastal impact, we've been issuing these bulletins to stakeholders. The Army Corps of Engineers has been funding this effort primarily to validate the WIS wave information study. And that's down on the bottom there. There's a portal where the wave climate model from the Army Corps of Engineers that's used to provide coastal engineering infrastructure guidance and the return times for extreme wave events is informed with this high precision, quality controlled, calibrated research grade data from CDIP. As a platform-based system, we collaborate with a lot of regional systems, and this, even though we have, as was mentioned earlier, somewhat orthogonal arrangements. This kind of works well because we connect as a national facility for this somewhat sophisticated instrument, and the regional observing networks have been able to help us identify and add stations in areas of particular need. So that's my time. Thank you.
Now we'll hear from Natalie.
Hi, thank you. This is work I've been developing with Paula here in CSS, two Paulas here at CSS, and Bruce Cornwell from Scripps, and Amy Bauer from Hui. And next slide, please. Okay. So the Gravis empirical modes is a technique. It's an empirical technique that basically uses surface information. And it's mostly sea surface height information from satellites and Argo data too, to project the three-dimensional thermohailing structure of the ocean. And so this study is a section of the Gulf of Mexico. There you can see a little bit of Cuba and Florida. So what I'm doing for this project is testing the sensibility of this technique to different surface information, basically, because so the background of this is that Paula and Bruce and Amy had been using satellite information and Argo data too, but I'm using the NEMO model just to test which other parameters we can use at the surface. And so with this, next slide, please. And so with this, I'll be using sea surface height, sea surface salinity, and sea surface temperature, just to get a sense of the distribution in my subsample area in the Gulf of Mexico, and see what can we do with this information and if we can actually use it in the SATGEM technique. So these are preliminary results, but basically what you're seeing here is a probability distribution of sea surface height on the left. And so we can see like the strongest line along the 0 and -2. We can actually relate these features to the loop current extension or retraction of the front of the current. And then there's another line that looks softer along 0.4 meters. And so that's going to give us information about the current and the state of the current and how we can use this information to project it with the GEM technique on the 3D structure. And well, I also did check the distributions for the surface salinity and SST. Next slide, please. And so what I did here, this is a lot of information, but it's useful because we can see the relationship between those variables, right? So on the first row, on the x-axis, everything is going to be SSH. And then we can see the relationship of sea surface height and with sea surface salinity, sea surface temperature, and temperature at different depths. So if you look at the last three squares, like last three columns, that's going to be the relationship of SST with SSH, with different temperatures at different depths. And you can see in some cases, it almost looks like a straight line. So in those cases, we're going to be able to project better the temperature or the thermohailing structure just by having SSH values. So all we need is a value at the surface. And again, here I'm using the NEMO model, but we can use satellite, we can use Argo data, whatever information we have at the surface to project the 3D structure. And then we also have the relationships with sea surface salinity, which is a mid-row. And that we can see that it's not very well defined. And then with SST, like the relationship is even worse, right? So we cannot really use SST to project the temperature and assume that that's going to be correct. So we're going to, from these results, we can say that SSH is a good parameter to use as sea surface information. And these kind of analyses are useful because, well, first it gives a lot. I had put like a QR code to a paper, but I see that it's not there. These kinds of analyses are useful because there are good estimators of ocean heat content, and they can also be used in operational models as boundary conditions. So like I said, these are preliminary results, but they give a good sense of how are these variables distributed and what is useful to use for the SATGEM technique. Thank you.
All right, so Natalie's presentation is recorded, so we're going to cue that up.
Hello, I'm Natalie Minacci from the University of Alaska Fairbanks Ocean Acidification Research Center. This is a service lab providing climate quality observations of the marine carbonate system. We collect data using two approaches: discrete seawater samples and autonomous sensors. This map shows the CTD stations we have visited. Remember, Alaska is big and hosts 5 of the 11 large marine ecosystems in US waters. We maintain 2 of the long-term National Ocean Acidification Observing Network sites, Geckoa in the Gulf of Alaska and M2 in the Bering Sea. Surface CO2 data is also collected using the sail drone. Data from these projects are public and archived with NCI OCADs. From here, they are synthesized into regional, national, and international products. Some of the first stops in this process are GLODAP for the CTD and discrete sample data, and SOCAT for the buoy and sail drone data. So why Alaska? Seawater around Alaska is uniquely vulnerable to OA due to naturally high CO2, low pH, and low aragonite mineral saturation states, or omega. The region's natural proximity to biological thresholds that may negatively affect marine species will continue to decrease with the accumulation of anthropogenic CO2 in seawater. Alaska's massive spatial footprint, low coastal infrastructure, and diverse cultures make it critical to form partnerships to maximize limited resources. Ultimately, these efforts are for people to understand and plan for the effects of climate change. This includes decision-making on mitigation and adaptation strategies, which are led by our data pyramid partners. Here I'm including a few recent products using GLODAP and SOCAT, led by Li-Ching Zhang and Jonathan Sharp. As the director of the UAF OARC, I am proud that our core mission supports the base of this data pyramid, the observations, and thankful to our partners and funding agencies to propagate this work to decision makers. So who is OARC directly accountable to? I would argue we are foremost accountable to Alaskans. Others in this workshop will share the how, when, why we connect climate data to society and our coastal communities. One point I'd like you to remember as we move forward is that Alaska is home to over 229 federally recognized tribes, and most of our coastal communities' populations are more than 90% indigenous. As we collectively continue to partner and produce products, we need to keep in mind the diversity of the people we serve, which will require a diverse number of tools, products, and education to remain resilient to climate change. I'd like to leave you with this picture of youth we are working with in the Gulf of Alaska and who will likely be leading some of these efforts in the future. Thanks so much.
Hi everyone, I'm Srilekha Jarugla. I'm currently a postdoc at Jet Propulsion Lab. I have a virtual poster on intercomparison of in situ and remote sensing surface salinity products in the global coastal ocean. Next slide, please. So why is coastal salinity important? So sea surface salinity in the coastal ocean can be used as a metric to interpret changes in hydrological cycle, especially in those regions where you have large river discharge happening. The stratified deep barrier layers have implications for air-sea interaction, tropical cyclone intensification, and also for primary production. Also, a recent study suggests that the variability of sea surface salinity in the coastal ocean is at least 10 times higher than in open ocean. So it's really important to observe and understand the changes in salinity in the coastal ocean. Next slide, please. We currently have 2 satellites measuring sea surface salinity. One is SMAP, which was launched by NASA, and the other is ESMOS, launched by the European Space Agency. And we have about 7 different sea surface salinity products from these satellites distributed by different organizations. So in this study, we do a comparison of how these different remote sensing surface salinity products compare with the in situ 5 meter average salinity observed by the profiles from the World Ocean Database. We show here different statistics of how they change as a function of distance from the coastline. These are averaged over the entire global coastal ocean. And we find that the number of co-locations available for in situ and satellite data comparison are few in the first 100 kilometers distance from the coastline. And this is also where you have large differences observed between the in situ and satellite products. This is mainly due to differences in the sampling strategies between the in situ observing platforms and satellites. And also there are issues like land contamination and radio frequency interferences happening. Next slide, please. We do an EOF analysis and we find that both the in situ and remote sensing products do a very good job of capturing the seasonal cycle in the sea surface salinity in the global coastal ocean, which is associated with the first two modes of EOFs. But they do have notable differences when it comes to capturing the non-seasonal variability, which is associated with the mode 3 EOF. That's what you're seeing in the last bottom panel here in the PC3 time series. Next slide, please. So overall, our study summarizes, emphasizes the need for improvement in the spatiotemporal coverage and also continuity of the near surface coastal salinity measurements in order to better validate the available remote sensing products and also to monitor the trends in the changing hydrological cycle. Thank you. Please take a look at the poster and reach out if you have any questions. Thanks.
Awesome. Thank you everyone for our virtual presenters. Can we give everyone a round of applause?